So hi everyone. Uh, the second unit, uh, design of combinational logic circuits in CMOS. The next topic, pass transistor logic, transmission, complementary pass transistor, and a differential cascade voltage switch logic circuit. Okay. In this pass transistor logic, what is it? So previous class we have seen the receiver logic and static CMOS logic design and all. The next one is pass transistor logic. See, uh, trans NMOS transistors are connecting seriously. Okay, in here they are connected in serious manner. The thing is, we can give the input at both the source, drain, and gate terminals, right? So you can give the input as the drain terminal, and we are getting output at the source, right? In previous NMOS transistors, we can give input only at the gate terminal. So here A and B, which is given in the drain terminal as well as gate terminal. Okay, so with this simple logic, we can achieve AB logic, A dot B. Okay, how this pass transistor work? Consider A and B are digital inputs, right? 1 and 0. So I'm giving B as 0 now. A is 1. What will happen when B is 0 in the NMOS transistor? hmm, it's open circuit, right? So A won't flow at the F. Now then, below that B bar, so in that above transistor B is 0, now B bar is 1. So your 0 will flow to the F. So based on that B input, okay, your output, whatever output we want to display at the output, we can select through this gate input terminals. Okay, this analogy will work in multiplexer logic. Okay, so pass transistor mostly used in a multiplexer based designs. We can reduce the number of transistors over here. Then what is complementary pass transistor logic? The pass transistor logic you have seen. Then if you are giving the a negative output, so it gives automatically CMOS logic, right? Previous gate I'm making here is AB. I'm connected with this inverter. So at the output of the AB, I'm getting what? AB bar. So right, that is complementary pass transistor logic output. The same thing happened in and I'm taking input as and NAND and OR and NOR, XOR and XNOR. Those are all the complement of each other. Okay, so both are separate circuits, right? But the common input for the gate has given B and B bar, B and B bar, B and B bar for all those three cases. So simply a simple design we can make it through this complex complementary pass transistor logic circuits. Then another important thing is a transmission gate. Okay, so this is the symbol for transmission gate. When it is connecting a series with the two NMOS transistors, that is pass transistor logic. Whereas in transmission gate, we can connect two transistors as in parallel. Okay, so in parallelly we can connect as a pass transistor logic, that is transmission gate. Here we can connect NMOS and PMOS, whereas in pass transistor we can use only NMOS transistors. In transmission gate we can use both NMOS and PMOS in a parallel structure. Transmission gate, XOR gate. Here, so what is the output of A, F, M1, M2, and here M3 and M4 transistors are there. What is the equation for XOR gate? We know that A bar B plus B bar A. So that is XOR gate of output. And this M3 and M4 transistor as well as M1 and M2 transistor, both those given as B, M2 the drain terminal has B and M1 drain terminal has B bar, and M3 and M4 gate terminal which is B and B bar. Okay, so with this simple structure we can implement the XOR gate operation used by both pass transistor as well as transmission gate structure. And differential cascade voltage switch logic. So with the help of pass transistor we may achieve um, XOR and XNOR. Is it right? Seen previously. Then what is the need of a differential cascade voltage switch logic? Okay. So CVSL seeks the performance of received circuits without the static power consumption. Okay. Here we may see that two pull down networks, right? B bar A and B bar A bar. So, right, upper you may have cross coupled with the two PMOS transistors. Okay. So one side we are getting a positive output, another side getting negative output, that is out and out bars. In a single circuit we can get both the complementary output. So the pull down network implements the logic function as in a static CMOS gate. For any given input pattern, one of the pull down network will be on and the other should be off. Why? Because A and A bar is there. So at a time any one of the pull down network only will be in active and another pull down network will be in inactive, right? The pull down network will be on, will put that output low, right? So when this low output turns on the PMOS transistor to pull the opposite output high. So the opposite output rises, the other PMOS transistor turns off. So the static power dissipation occurs here. To reduce that static power dissipation, we are going to this DCVSL logic. So I hope you understand that. To implement DCVSL, we are having pull down networks, two pull down networks with cross coupled PMOS transistors. Okay. So conclude this lecture. Pass transistor logic, we may give the input to the drain and source terminal as well as gate terminal, so that we are reducing number of transistors when compared to CMOS, and both are connected in a series manner. Whereas in transmission gate, both PMOS and NMOS are connected in a parallel way. NMOS and PMOS are connected in a parallel structure, so that we can design any combinational logic circuits using that transmission gate. So example you have seen transmission XOR gate logic, etc. And after that DCVSL to reduce the static power consumption and complementary operations. Okay. So I hope you understand these three concepts. Thank you.